Hello and welcome to section 3. In the first two sections we've been talking about graphing quadratic functions and how to solve quadratic equations by graphing the functions. And when we solve a quadratic equation, we mean that we are finding the x-intercepts or the zeros or the roots or the solutions. All of those basically mean the same thing. So what we're going to focus on today is another way of solving, which is by factoring. That's why in our last video we reviewed the different techniques of factoring, because for this section they are assuming that you know them all and that you can use them correctly. So we're going to learn how to write quadratic equations in intercept form, which is actually the same as factored form. And then we're going to solve by factoring. So we have two main skills today. So we're going to make sure that we know what factored form means, and we're going to review how to FOIL, although we kind of did that in the last video already. So remember that when you FOIL is a method for multiplying two binomials. So if I have x minus 6 times x minus 2, I do my first term, so x times x. My outer ones, x times negative 2. My inner ones, negative 6 times x, and my outer ones, negative 6 times negative 2. That is review. So FOILing is what allows me to multiply two binomials, and also, if you remember from our previous video, if I've factored something and it comes out as two binomials, I can FOIL it to get back to my original quadratic and see if it is correct or not. So what is factored form? We talked about this yesterday as well, but the factored form is when I write my quadratic equation equal to 0, and then on this side I have everything written as factors. So sometimes there's a constant out in front that's called our a value that determines, remember, if the parabola opens up and down, if it's wide or narrow. And then I have my different factors. So here x minus p is one factor and x minus q is another factor. In those factors, p and q represent the x-intercepts of the equation. So if we look at this graph over here, we have an x-intercept or a solution here that's 2, 0. And then we have an x-intercept here that is 6, 6, 0. So the standard form would look like this: x squared minus 8x plus 12 equals 0. But the factored form looks like this. One of my x-intercepts is 6, so the factor is x minus 6. And one of my x-intercepts is 2, so the factor is x minus 2. And we will see why that works in just a minute. So we're going to use that idea that if I know what my x-intercepts are, I can write the factors. So notice the x-intercept was positive 2. The factor was x minus 2, right? We're going to use that fact to translate this sentence into a quadratic equation. So it says write a quadratic equation in standard form with roots. Remember, roots are also x-intercepts. Roots of positive 1/2 and negative 5. So the pattern is this: x minus p times x minus q. Those roots go in the factors. The negative is just part of the formula, if we can say it at this point. And again, we'll see a little bit more why in a second. So I'm going to say, okay, x minus 1/2, right? So my first root goes there. And then x minus negative 5. And my negative 5, my other root, goes there. Then I'm going to simplify a little. X minus 1/2 times x plus 5, because it's x minus negative 5. And then we're going to FOIL. So I do x times x, which is x squared, x times 5, which is 5x. I'm going to write this over here so you can see all of the terms. Then negative 1/2 times x is negative 1/2 x. And negative 1/2 times 5 is negative 5/2. So what they've done here is they've already added 5x minus 1/2 x. Remember that 5x is 10 over 2x. So 10 halves minus 1/2 is 9 halves. That's how we got that fraction. And then what they're going to do, let me actually show it to you back here on the previous slide. In standard form, we usually want a, b, and c to be integers. So I want to clear out these fractions. So I'm going to multiply both sides of my equation by 2. So I'm going to get 2x squared. Then I'll do 2 times 9 halves, so that'll give me 9x. And then 2 times negative 5/2, which will give me negative 5. So my equation ends up looking like this. 2x squared plus 9x minus 5 equals 0. So this would be one example of a quadratic equation that would have roots or x-intercepts that are positive 1/2 and negative 5. All right, following the same pattern, you guys try this one. Okay, you should have gotten b, 4x squared minus 17x minus 15 equals 0. And there's the work if you need to stop for a second and check that out. All right, what we're going to do now is talk about the zero product property. This explains kind of why we can write things in factored form the way that we did. So if I have two real numbers, a and b, if I multiply them together and it equals 0, one of those numbers or both of them have to be 0. For example, if 3 times x equals 0, I know that x has to equal 0, otherwise 3 times x wouldn't equal 0. The same thing works with quadratics, with factors, okay? These two factors are connected by multiplying. The adding and the subtracting are contained inside the parentheses. So I basically have x plus 3, that's like my a, and x minus 5 is like b. So I have a times b equals 0. That means either a, which is x plus 3, has to be 0, or b, which is x minus 5, has to equal 0. If that's the case, and I were to go ahead and solve those, so if I were to subtract 3 from both sides here, I would get x equals negative 3. And if I were to add 5 to both sides here, I would get x equals 5. So my x-intercepts here would be negative 3 and positive 5, but the factors are x plus 3 and x minus 5. That's why when we plug them into the factors in the previous examples, we ended up with the opposite signs. It's because of the zero product property. So let's take a look at how we would do this. We're going to start with this example, 9y squared plus 3y equals 0, and we're going to solve it. Of course, we could graph this, but another way to do it would be to factor. So we're going to factor out our GCF here. Our GCF between 9y squared and 3y is 3y. I can rewrite 9y squared as 3y times 3y, and 3y I can rewrite as 3y times 1. So when I factor that out, when I undistribute it, I can rewrite it as 3y times the quantity 3y plus 1. So this is now in factored form. And since it's in factored form, I can use the zero product property. So what I'm going to do is I'm going to set each factor equal to 0. So either 3y has to equal 0 or 3y plus 1 has to equal 0. And then we're just going to solve each of those. Here I divide both sides by 3. And I get y equals 0. Here I subtract 1 from both sides and get 3y equals negative 1. And then when we divide by 3, I get y equals negative 1/3. So that means that those 2 points would be my roots or my x-intercepts or my zeros. All right, let's look at this one. This is another GCF example. There's my original equation. Notice it's equal to 0. We always want to set it equal to 0 before we start factoring. Here the GCF is 5a. So we're going to factor out the 5a, and that gives me 5a times the quantity 5a minus 4. Then, since it's factored now, that's factored form, I set each factor equal to 0. I think they forgot. They have a typo here. That shouldn't be a 5, right? Okay, sorry, when the PowerPoint has typos. So I end up with a equals 0 or a equals 4, because this 5 should not be there. It's actually 5a times a minus 4. So I get 2 x-intercepts, zeros, roots, which are 0 and 4. So if I was to graph my parabola, I know I would have an x-intercept here at 0, and I would have an x-intercept here at 4. All right, you guys try this one, factoring with the GCF. All right, your answer here is D. So those would be my 2 x-intercepts. Remember, those represent the points 3, 0, and 0, 0. And here's the work if you need to look at that. All right, let's try one with a different kind of factoring. Here I have the quadratic x squared minus 6x plus 9 equals 0. Well, I noticed that my first and last terms are perfect squares. So if you remember the pattern for perfect square binomials, or perfect square trinomials, you might recognize the pattern that you need to factor this with. We're going to talk a little bit more about that pattern specifically in a future section. If you don't remember how to do that, then we would factor this like we did the quadratic trinomials in yesterday's video. So we would be looking for two numbers that multiply to positive 9 but add up to negative 6. In this case, those numbers are negative 3 and negative 3. So negative 3 times negative 3 is positive 9, and negative 3 plus negative 3 is negative 6. So what we're going to do is we're going to rewrite this trinomial as x minus 3 times x minus 3 equals 0. Notice that both of the factors are the same, right? So after I get it into factored form and set each factor equal to 0, it's going to give me the same thing. That means there's only one x-intercept. If you remember that picture we looked at the other day in one of our previous sections, that means that it only touches the x-axis at one point, and that point is the vertex. So the point 3, 0 here is my x-intercept, but it's also my vertex. So when this happens, we kind of have two solutions that are both the same, so we really only have one answer, but we call that answer, that solution, that x-intercept, a double root because it appears in my equation twice. Okay, let's try this one. Remember I told you earlier in this video that we always need to get it equal to 0 before we try to factor. So we're going to subtract, oh my goodness, this is full of issues. We're going to subtract 36 from both sides and rewrite this as y squared minus 36 equals 0. You should recognize this pattern from yesterday's video. That's the difference of squares because y squared is a perfect square and 36 is a perfect square. So we can rewrite this, we can factor it as y plus 6 times y minus 6. Then I take each factor and set it equal to 0, and I solve. So here I end up with two x-intercepts, negative 6 and positive 6, or two solutions in this case, two roots, two zeros. All right, try this one. Okay, the answer here is 8. This only has one root, which is 8. It's a double root because this quadratic is a perfect squared trinomial. So when I do my factoring process for quadratic trinomials, I find out that the two numbers that multiply to 64 and add up to negative 16 are negative 8 and negative 8. So when I solve, I get x equals 8 twice. So I really only have one solution, but it's called a double root. All right, factoring trinomials. This is back to what we were doing before. Basically the same as the last example we just looked at, except this is not a perfect square trinomial because 15 is not a perfect square. So we're looking for two numbers that multiply to negative 15 and add up to negative 2. So factors of negative 15 would be like negative 1 and positive 15, which would add up to 14, or 1 and negative 15, which would add up to negative 14. Negative 3 and 5, which would add up to 2, and 3 and negative 5, which would add up to negative 2. And we're looking for this set of factors that adds up to negative 2, but multiplies to negative 15. So our two numbers are 3 and negative 5. So we rewrite our equation. Notice here's my 3x and my negative 5x, just like we looked at yesterday. And then we're going to group the first two and the last two. We're going to factor the x out of x squared plus 3x, factor a negative 5 out of 5x plus 15, and then the x plus 3 is now my common factor, so that gives me x minus 5 times x plus 3, and then I set each one of those equal to 0, and I solve, and I get x equals 5 or x equals negative 3. Those would be my two roots or my two x-intercepts. All right, what do we do when there is a number a that is not equal to 1? Well, remember that we multiply 5 times 24, so I'm looking for two numbers that multiply to 120 and add up to 34. This takes a long process. I'm not going to go through the whole thing right now, but here they have all of the factors of 120 listed out. The ones that add up to 34 are 4 and 30. So we're going to do the same thing we did in the last example. We're going to rewrite our middle term using 4x and 30x, group, and then factor an x out of the first two terms and a 6 out of the second two. And there should be a 5 right here. And that gives me x plus 6 times 5x plus 4 equals 0. So these would be my final answers. I want you guys to try this one.